Hey kiddos, welcome to week number 6. Hopefully you're having a good day. Today, what I'd like us to work on is to take a look at how there was a force acting between our pith balls in the demo that I did last week without the pith ball and the wand actually touching, and how there was a force exerted between the two metal pieces of foil in the electroscope simulation without those pieces of foil actually touching. We'll be able to determine the direction of an electric charge, calculate forces due to charges, and also compare gravitational and electrostatic forces in fields. And this is a comparison that the IBO wants you to be able to explicitly make, and so I'm going to give you a graphic organizer to do that comparison. All right, you guys, let's get started. All right, so last week I did a demo. We looked at 2 different types of electroscopes, and I want to talk about the Pith Ball electroscope first. So remember, the Pith Ball was that little piece of styrofoam that was dangling off of the thread, and we used our charge wand, which we charged by friction, and we noticed that the wand attracted the Pith Ball, and I want to talk about why that is. But first I want to talk about electric charge in general. Okay, so electric charge, what's its abbreviation? Oops. It's its abbreviation and the unit. Okay. Electric charge, you would think it's abbreviated with like a E or a C or something, but actually electric charge is abbreviated typically with the lowercase letter Q. Okay, what I just drew there, that's how I draw Qs. You might see them drawn like this, something like that. So electric charge is a letter Q. Okay, sometimes I use a capital Q and a lowercase q to kind of differentiate between 2 charges, but Q is the letter that we're going to use for electric charge. Okay, the unit of charge, this is not a unit like a Newton that is made up of other things. This unit is a base unit. This is a capital C. And the unit of electric charge is the coulomb. Okay, so just like when we studied Newton's laws, the unit of force was a Newton. When we study electric charge, it was investigated by a scientist named Coulomb. Okay, and so the law that we will learn about later in quantifying electric charge and the forces between charged objects will be called Coulomb's law. Now, a lot of times we use some common abbreviations when talking about charge. Okay, so sometimes you'll see, instead of coulombs as a unit, you'll see lowercase nc, and that is nano coulomb. Okay, and a nanocoulomb, nano is a SI prefix, meaning times 10 to the negative 9. So a nanocoulomb is times 10 to the negative 9 coulombs. You'll also see this abbreviation. So remember the Greek letter mu, we used it for the coefficient of friction. It's also an SI prefix that means micro. So mu c means microcoulombs. And micro is times 10 to the negative 6 coulombs. All right, so I asked you to take a look at the electroscope simulation, and you could see positive and negative charges and how they moved or didn't move within a metal electroscope. What you should have seen is that positive charges stayed put and negative charges were moving around. Okay, and that makes sense based on our understanding of the atom, right? Positive charges are within the nucleus, which is locked. So those positive charges are locked within the nucleus of an atom. Negative charges are loosely bound to an atom. They're out in those energy level orbitals, and so they can be transferred, and they can be repelled or attracted. Okay, so when we're talking about electric charge, if you have an even number of charges, so for every negative charge there's a positive charge, then that means the object is electrically neutral. Okay, the positive charge cancels the negative charge and the object becomes electrically neutral. If you've got more positives than you have negatives, then an object has a positive charge, right? A net positive charge, right? Because one of these positives isn't canceled out by a negative. And then if you've got more negatives than you have positives, then you'll have a net negative charge. Okay, so let's take a look at what happened with our pith ball electroscope. So let's say we have a neutral pith ball, which is what we tried to have. Okay, and then we had a negatively charged wand, okay, which over the years is typically what happens to the wand. It becomes negatively charged. Okay, so what's happening within the pith ball? Next step, so this is step 1. Step 2, when that wand gets close to the pith ball, this bunch of negative charges repels all of the negative charges within the pith ball. That makes the right side of the pith ball have a net positive charge. The left side is more negative now because all of the negatives were repelled over. And since this side of the pith ball is positive and opposites attract, the positive side of the pith ball is attracted to the negative wand. They attract. Okay, they will attract and then touch. All of the negative charges within this wand here will perceive a positive region in the pith ball, and some of them will hop over to the pith ball to try and neutralize out this region that is positive. Okay, try and neutralize that out. Yes, I know there are negatives over here, but this region is positive right now. Even though this entire pith ball is technically electrically neutral, the right-hand side of the pith ball is positively charged. Okay, and so those negative charges always want to go and neutralize a net positive charge. Okay, charges always want to neutralize. Okay, so when that happens, and then we separate the wand from the pith ball, all of the charges will end up evening out in the pith ball. This pith ball has a net negative charge now. The wand still has a net negative charge. That charge is smaller than it used to be, but now we've got a negatively charged pith ball, a negatively charged wand. Like charges repel, right? And so now the pith ball repels. And that's what we observed in the demo from last week. All right. So let's take a look at what happens. Can we use a positively charged wand? Yeah, it's perfectly reasonable that wand could be positively charged instead. So we'll do steps 1, 2, 3, 4. Step 1, let's say we have a positively charged wand. So when rubbing the fur on the wand, maybe the fur took electrons away, and that would have left the wand a net positive charge. And we have a neutral pith ball. Okay. Then we bring that wand up close. It's positive, so the negative charges in our neutral pith ball are attracted to the side of the pith ball that is nearest the wand, right? Those negative charges are the only things that can move, right? They move over, they're attracted to all of this positive charge. That leaves the right-hand side of the pith ball acting negative, and the left-hand side, the electrons are away, and so it acts like a positively charged side. This negative side is attracted to the positive wand. They attract, they touch. Now we're down here in step 3. Once they touch, the negative charges that are on the right-hand side of the pith ball, they want to work to neutralize this positive wand. So some of them hop over to the wand, giving negative charge. If 2 charges hopped over, 2 of these positive charges would be neutralized. And we see that here, positive, 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 2 negatives. So that would mean this wand would have a positive charge of +2 now. So this has a weaker positive charge. The pith ball lost 2 of its electrons, and now it is no longer neutral. Some of its positive charges aren't canceled out by negative charges, so it has a net positive charge. A positive object and a positively charged object repel each other. Okay, so a couple of the things that maybe we noticed or we should discuss in debriefing the demo that I did. We should discuss that like charges repel, opposites attract, and neutral objects are always attracted to charged objects. Right, that pith ball started out neutral, and it was attracted. Okay. All right. So would this work the same if my wand had been made of metal instead of black plastic? It actually wouldn't have, right? So black plastic is what we call an electric insulator. Okay. You can put charges on that wand, right? I can put charges on that black plastic, and an electric insulator like that plastic or rubber or glass, they inhibit the movement of accumulated charge, right? So what that means is if charge is placed on an insulator, it stays put and can be measured. This is a common misconception. Insulators inhibit the flow of charge. So that means charges can stay put and be measured or exert forces on other charged or neutral objects. So that's what we were seeing. If you were to do the same experiment with a metal rod, which is an electric conductor, right? Metals are an electric conductor. You could still put the same amount of charge on the metal conductor, but conductors easily allow for charge to flow or move. So any charge that's placed on that conductor will spread out evenly. And when it all spreads out, it can't be measured. It's not accumulated, and it can exert forces on other objects.